Welcome to InventBox, where the solution is right around the corner. This is Darius, and this video is possibly the most important, covering some of the most important concepts in WebGL, and that is lighting. So as an overview, I am first going to talk about something called surface normals, and we will discuss diffuse lighting in this video. We'll jump into the code and get our textured cube to then be lighted. Now, I've changed the texture image to what I call the event box in a box, and it looks pretty fantastic, I must say. However, as it's rotating, you'll notice that the corners disappear as they're in front of you, and you can't see any edges or lines that are internal because there's no lighting, and all of those pixels are exactly the same color. So we'll be changing that, but first I want to make a quick comment about the server situation we've got. This is running on localhost right now, and it's in the past videos I've been using that Node.js simple HTTP server, but on this video I'm using an entirely different server. It's the Python, the one that's built into Python, and you call it with python-m http.server and then give it a port. And I'm doing this just to show you that you really can use any server you want. In fact, these examples will work just opening the file locally in your browser. However, I've been putting it on a server through all of the tutorials just so that if we ever wanted to do some AJAX or something else that requires being on a server, we will be good to do that. Enough said, let's get into the meat of this. So the first topic is surface normal. And the image shows quite well that it's simply a vector that is perpendicular to a surface and simply indicates the direction that that surface is facing. Now, this is important because there's actually for every surface there's two possible normals, since a surface has two faces. So the normal also communicates which face you're talking about. Additionally, when something is normalized, it has a length of 1. That's because you don't need any information about magnitude when you're talking about what direction something is pointing. Now, we are specifically focusing on a type of lighting called diffuse lighting, and diffuse lighting is determined by the angle from the surface to the light direction. So let's look at a visual of what's going on here. So supposing that the light direction is coming in at this sort of downward and to the left, let's imagine it looks like our sun would be about where the G is, okay? So for every surface, the brightness is calculated using the same light direction, and then based on the angle we will figure out how bright it should be. So obviously this top facing surface will be the brightest because the surface is almost directly pointing at our sun, and the ones on the bottom and on this side are less than 90 degrees, and they're completely black because no light obviously can get to the left or the bottom face. So the rule or the pattern we see is that angles between 0 and 90 degrees will have no brightness at all, and as soon as you hit 90 and start climbing towards 180, you approach a fully lit surface. And this behavior actually models the function cosine. So if we take the cosine of the theta between the normal and the light vector. It will give us a useful brightness percentage that we can assign to a surface. So how do we get the cosine of the angle theta between two vectors? We will use something called the dot product, and that definition of a dot product is that the dot of some vector A with some vector B is equal to the length of A times the length of B times the cosine of theta. Of course, the last part is what we want, but if we remember that since all normals have a length of 1, they will multiply together and sort of drop out, and we get this equivalency that the dot A dot B is just equal to the cosine of theta, which means if we dot the light vector with the surface normal, we will get the brightness. How convenient. Just food for thought. There's also another way to multiply vectors, and that's the cross product, and the cross between two vectors is equal to the sine of theta instead of the cosine. We're not using that in this video, just thought I'd throw it out there. Now it's time for some code. Now I'm starting off about where we left off in video number 10, texturing. I replaced the image with the invent box. Let's quickly describe what we're going to do here. First, we need to describe all of our normals for each vertex. We'll create another buffer and another vertex attribute and give that information to the vertex shader. We'll have the vertex shader calculate the lighting, which will pass that information onto the fragment shader that will recalculate the color based on the lighting brightness. Along the way, we'll need to mess with another type of matrix called a normal matrix, which will transform all of our normals as our model rotates. So let's get to it. We're going to create another array, which I will call normal data, or normal data. And I will utilize the repeat helper function, which you specify we want 6, since we have 36 vertices and 6 of them to a face, and on any given face all 6 are pointing in the same direction, so it makes complete sense to just repeat that normal 6 times. And as far as which face we're starting with, it has to align with the position, the way we've defined it, the convention that we've already done with the position. So I'm going to copy this little blurb so I can see it, and this is front, left, back, right, top, underside. And I put it in the wrong place, so okay. For the front side, that is actually in the positive Z direction, because it's towards the camera, that right-handed coordinate system. So X is 0, Y is 0, and Z is positive 1. And that's done. So the ordering, if you're typing this out yourself, is plus Z minus X minus Z plus X plus Y and minus Y. And it's important to note that for any of these 3D normals, the length is 1 already, so we don't have to normalize it. It already is a normal. I'm just going to copy what we've got for the UV buffer and make a normal buffer. And again, this is the mechanism by which we get our data into the shaders. Along with that theme, let's create another definition for the vertex attribute. I'm going to call it normal in the program. And we will bind the buffer and then describe it. It is simply a 3-component float. Okay, let's see what we've got in the shader. Again, it's a 3-component float. Okay, so now the task is to use the dot product somehow to calculate a per vertex percentage of brightness. And that will depend on the current light direction, which way the light is facing. Let me bring up that image. Yes, so the normal attribute is the red arrow. We have to create a light direction, and I'm just going to do this very simply by defining a global constant vec3. So it will be the same for all vertices. And I'm going to move it up 1 unit, that's y, and also 1 in the z, which is away from the camera. Or sorry, away from the screen. I shouldn't say the camera, because the camera is actually sort of a mathematical abstraction, and we have it located somewhere else. That depends on your view matrix, right? Okay. Now we need to fix something here, because unlike our normals, this light direction is not currently normalized. In fact, I can tell you right now it has a length of the square root of 2, which is not okay for our math. Remember, we need both of them, the light direction and the normal, to be normalized so that our math simplifies, and we can just use the dot to get the cosine directly. Okay. So the, I don't know, maybe the intuitive thing here would be to calculate the, I'm going to, instead of storing it direct, let's see, so yeah, let's do this. I was saying the intuitive thing would be to calculate the diffuse brightness by taking the dot between the normal and the light direction. And this would work, kind of, except that our box may have rotated, and therefore the normals would be different than just what's coming from this JavaScript array. And so if our normal has rotated, or sorry, if our box is rotated and our normals have rotated, then we need to apply a transformation on them all, so that you would say that the normal has now been put into world space, where it reflects the correct orientation that the surface is actually facing, that you would see on screen. And to do that, we are going to use another matrix called normal matrix. And of course, this will store information about the current orientation of the object in the world. and then we will create a world normal, a modified version of the original attribute, and it will be the result of the normal matrix times the given normal, but since the matrix is a 4x4 and the attribute is only a 3 component vector, we have to temporarily convert it into a 4 component vector just by setting the last component to a 1. That works just fine. And then finally, since the result will also be a 4 component vector, we only care about the last 3, so we will selectively choose just .xyz. And now world normal will store the direction that the surface which this vertex is on is currently facing, even if it's been rotated. That's pretty cool. Now we need to account for another special case here, and that's the dot product can return a negative number, which is not at all useful to us because a negative brightness makes no sense. It would just be black. Everything, back to that image here, you can see that everything that's less than 90 degrees is black, no matter how, if it's 20 or 50. For that reason, we use the max function and just bound it to values greater than 0. This way, when it turns a negative number, it will just set it to 0. Okay, we've calculated the per vertex brightness. We now need to pass this on to the fragment shader. I'll call it V brightness. And currently the brightness is determined just by the diffuse value, the diffuse lighting. That should be it for the vertex shader. So quick summary, we added a normal attribute. We also added a normal matrix, which we haven't talked much about yet, or we haven't created it yet in the CPU side in the JavaScript. But we sort of understand how it functions, and it transforms the normal given by the attribute. It transforms it in a way that reflects how your object is currently oriented. And we use the dot product on the two normals, and we constrain it to never be negative because we don't use that functionality, or it doesn't make sense in our case. And we pass on the value. We will accept the brightness in the fragment shader side. Now we need to apply this brightness to the color we got off of the texture. So let's rearrange things a little. The color is a vector of 4 components because there's an RGB and an A. And we're calling it a texel because it's a pixel of a texture. It's just graphics programming lingo. We want to only modify the RG and B, or the first 3 components, by the brightness and not the alpha, because if you think about it, changing the brightness of a surface, changing the lighting, shouldn't also change how transparent it is, which is what the alpha is for. So we want to make sure we don't tamper with the alpha. that's it for both shaders. The fragment shader is probably the easiest to understand. There's not much going on there. Now, we've added another uniform, so let's get the location of that. I always just name the variables in JavaScript the same as what they are in the program, or in the shader, because that is easier to think about. Okay, so let's create this. The last thing to do actually is to create and store a value in the normal matrix. Now, up to this point, most of what I've been doing has been pretty intuitive, fairly easy to explain. The normal matrix is a little bit, but the math is a little more intense, and if you want a complete understanding, you will want to go online and look at some pictures and read some articles. So we'll just create an empty matrix at first, and it will stay that way until we start running the update, until we start updating our frames. Because remember that the normal matrix is dependent on the position or the orientation of your model. So we'll wait until after we've calculated our model view and projection matrices, and then we do an invert. And in the JavaScript matrix API, remember the first argument is the receiving matrix, which is normal matrix, and we're going to start with MV matrix. Okay, so it's going to start with MV matrix, and then it will invert that and store it in normal matrix. So the normal matrix has a inverted version of the model view matrix, and then we transpose the normal matrix. And transposing, so if you look at the word, it looks like trans is to change and pose is like position. So it looks like change position, and it's not the same as translate. It's not talking about moving your model around. It actually means rearranging the rows and the columns in the matrix itself. So when you transpose it, the rows become columns and the columns become rows. That's probably the most, I don't know, that I won't say it's the best definition, but that's another thing that you can look up on Wikipedia or something, get a real mathematical definition. So we've just inverted it and we've transposed the rows and the columns, and that's actually all we have to do. We'll upload this guy. And we will see if it works. Should be ready to give this thing a spin. I did catch something here. This should be a times equals. It's actually very important, because if you don't do times equals, then the compiler will actually optimize away your V brightness, because it won't be actually using it to compute the result. So that's very important. So let's see how it looks. Right now there's no lighting, and we'll give it a refresh, and that is pretty neat. You can see that it goes completely dark at some point, just like our drawing, and something about this looks a little unnatural, it's not wrong programming wise per se, but there is something that we can do to make it even more visually appealing, and that's because in the real world you almost never have surfaces that are 100% black, unless you're in a cave, because you've got some amount of light bouncing around off of objects and illuminating everything just a very small amount, sort of a minimum baseline. So this is called ambient lighting, and we can add it very, very easily. All we have to do is add, like 10% onto this V brightness. Now I will extract this into a variable so we can play with it and know what it is and not just have a number floating around in there. And just for effect, let's change this background color. It's not terrible, but we can do better. I want to do a linear gradient. That goes from F0, F8, FF to black. Very nice. I would say that is rather impressive. So this is the end of the tutorial. I think this is a good stopping point. So in quick summary, we looked at surface normals and created those for our box, fed those to the shaders, and then we learned a little bit about the normal matrix and transforming your normals so that it matches the rotation of the object. And also the dot product. We utilized the dot product to get the cosine of theta, which happened to be a good model for us to calculate the lighting. And that again is diffuse lighting that we talked about, and of course ambient lighting we added just as a final touch so that the surfaces never go completely dark. Well, that is the end of this tutorial, but I have one announcement to make before I leave you guys, and that is that the Invent Box, as of this video, the Invent Box YouTube channel now also has a GitHub repository for the Learn WebGL videos, and all of the code from the past videos is up, and this will continue to be added to as more videos are made. So for example, I can go check out everything that you just saw me type in main.js. Pretty cool. So if you've been struggling to follow along, or as the code size of the files is getting bigger, all of these examples should work right out of the box. And if not, please leave a comment either on YouTube or create an issue on GitHub would be even better, and I will take care of it. And with that, I will leave you guys. So thank you for watching.